Hello all, my name is Natalie Hollon and I'm in the 102 section of Chem 4000, and today I'm going to be presenting on an article that I researched about titled The Ultramicro Enzyme Assays in a Capillary Electrophoretic System. Let's get started. Here's a general overview of what I'm going to be discussing today. First, I'm going to be talking about the scientific purpose and the reason the experiment was conducted. Then I'm going to be going into the introduction of how the experiment was conducted. Then we're going to talk about the electroosmotic flow in a capillary and how it works. Next, we're going to talk about how we were able to detect our product and what methods we used for that. Lastly, we're going to draw some conclusions about the experiment as a whole. I'm going to talk about what citations I used, and then if there's any questions, I will post my contact information if you would like to reach out to me. Okay, so the scientific purpose of this article was using an enzyme model and conducting an experiment to determine how much product it could accumulate. So in this case, we are using the G6-phosphate dehydrogenase as a model enzyme because it is found in most animal tissues and microorganisms. It also catalyzes the first reaction, which can be readily assayed. Next, I'm going to talk a little bit about enzyme assays and how they're conducted. So there are 3 steps to assay an enzyme. First is the initiation of a reaction where the reactants are rapidly mixed together. Next, there is a period of incubation where the product and the reaction accumulates. And lastly, you want to find a method to be able to measure the amount of product that was formed during the incubation period. Mixing of the reactants and incubation can occur in one of 2 ways. The first way is known as the zero potential or stopped flow method. At zero potential, the product would accumulate in a single mixing zone because the electrokinetic and electrophoretic transport would not occur. This corresponds to a fixed time reaction in a conventional enzyme assay. The second way would carry out an assay at constant potential. In this method, the reactants are mixed and continuously separated from the product. The issue with this method is that the enzyme catalysis occurs much faster than the rate of separation. Therefore, under constant potential, enzyme assays must be carried out in short, fixed time assays. Constant potential showed the most promising results, and that was what was primarily used for our experiment. This image here shows the capillary used to carry out the enzyme assays. In order to use the capillary, there's 2 steps that you need to do in order to prepare it. The first step is washing the capillary with sodium hydroxide to deprotonate where the electroosmotic flow is going to occur. Next, you want to wash the capillary with a buffer. The higher the pH, the stronger the charged double layer is, which would mean the higher the osmotic flow. So using a buffer with a high pH ensures that you have a strong double layer. The negative charge will produce the osmotic flow that transports the liquid from the anodic end on the positive side to the cathodic end on the negative side of the capillary. The capillary is placed in a substrate buffer before injection of the enzyme. An enzyme assay begins by loading the enzyme into the capillary electrophoretic system by electrokinetic injection. As soon as the enzyme is loaded, the reactants mix and the reaction can begin. Product formation is continuous until all of the enzyme exits the system. Therefore, this will continue to occur until all the enzyme is used up. For product detection, an ultraviolet variable wavelength detector was used. The product formed from this catalysis reaction is NADPH. As you can see from the reaction here, this is our product when you mix it with our enzyme of interest. NADPH has a maximum absorption of 340 nanometers, and this is what we were looking for when we detected it on the UV vis. The absorbance spectrum of NADPH is readily different from any of the assay reagents or the enzyme. Here, in this reaction, you can see how the product is created. Each of these graphs were conducted under constant potential, which is how the reaction is initiated. Figure 1 shows the predicted model of what the capillary electrophoretic enzyme assay would look like when the amount of enzyme in substrate is greater than the amount of product. Figure 2 shows the actual results of the capillary electrophoretic enzyme assay between the injection and the start of electrophoresis. Both graphs share a similar peak. As you can see on the graph on the left, where there's a B over top the peak, that corresponds to the peak, the high peak that is shown on the graph to the right. And this just shows the amount of product or NADPH that was accumulated before electrophoresis even began. And this goes to show that we were on the right track before conducting the experiment. In conclusion, small quantities of an enzyme may be detected in a capillary electrophoretic system by carrying out the assay in the capillary. The graph to the right shows the dose-response curve with the amount of product on the y-axis and the concentration of the model enzyme on the x-axis. These variables show a linear relationship and therefore tell us that the experiment was conducted as predicted. Here are the citations I used for my presentation. I wanted to give out a special thank you to Gracie for her patience and for sharing her research with Henley and I. I know we both really enjoyed getting to see what she was doing and learning more about her research. This here concludes the presentation. If you have any questions regarding the material, please do not hesitate to email me. My email is shown here on the screen, and I'd be happy to answer your question to the best of my ability. Just wanted to say thank you so much for tuning in and hearing more about the article that I researched this semester, and I hope you have a wonderful rest of your semester online and that you're staying healthy and safe during this unsure time. Thanks again.